Okay, well, thank you. And thank you all for turning up at the various hours you are turning up. The main theme of the lectures is going to be the sort of geometry of the Hitchin integrable system and its variants. In particular, the sort of geometry of, because these integrable systems end up being flows of line bundles over Riemann surfaces, the sort of general geometry of those flows and how they can be integrated, and some nice links to the geometry of surfaces. That being said, as I was sort of going through the various sides, these Hitchin equations, or the Hitchin systems, are reductions of the Yang-Mills equations from 4 dimensions. And it struck me that there's a whole series of places in which, if you're looking at various reductions, the geometry of Riemann surfaces and line bundles come in and sort of and obtrude in various ways. So I thought I'd sort of go through and give you some examples to start with. So that's the subject of the first lecture. So the material is quite classical. So wait a second, now the damn thing doesn't want to move. Oh dear. Talking too much. Sorry, it doesn't want to thaw. No? Excuse me, it's frozen. Ah, there it thawed. Good. Okay. So the theme of this is 2 out of 3 ain't bad. You'll see why, and an abundance of curves. So we're going to start with a connection on a vector bundle, unitary bundle over R4. And of course, the equations we're going to get are conformally invariant. So you can eventually place them over S4, and for boundary conditions, that's extremely useful. So you start with a connection, which you can just write as a covariant derivative. So in the ith direction, you've got di plus ai of x. And these are unitary, or not unitary, but sorry. Skew-Hermitian. And you've got a connection, and it's got a curvature, which is written here. And the nice thing about R4, or in fact, many dimensions, is but in particular R4, you have a Hodge operator on forms, which is defined in general this way, and on 2 forms sends 2 forms to 2 forms, and on 2 forms has the square, that's the identity. And so you can split things into eigenspaces, and your curvature, which is this endomorphism valued 2 form, will have a self-dual piece and an anti-self-dual piece. And why is this interesting? Well, if you're thinking variationally, you're minimizing an energy, which is a norm squared of the curvature. And there's a topological degree once you've compactified things to S4, which is the difference of the f plus and f squared plus and f squared minus. And so the minimal energy configurations are either self-dual or anti-self-dual. Oops. Now, how do I get out of this? Nope. Oh, this is terrible. There we go. Okay, so now you want to make this interact with a complex structure, because the theme of this is complex geometry. And so forms, or choose a complex structure on R4. So I've just written 2 complex coordinates, Z1 and Z2, and the 2 forms split into bitypes. So they're the DZ, 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 DZ bar, and dz bar, dz bar. And with this, the self-dual forms are the two zero forms, the 0-2 forms. And in the 1-1 forms, it'll be the multiples of the Kähler form. And the anti-self-duals are the orthogonal complement in the 1-1 piece. So if the connection is anti-self-dual, there's no 0-2 curvature, right? All the self-dual bit vanishes. And so there's an integrable d-bar operator. And so how can you're getting a holomorphic bundle. So one of the ideas is to flip this around. You take a holomorphic bundle and you choose a Hermitian metric. And there's a canonical connection once you fix those two structures. That's the Chern connection. And it has you get back the holomorphic structure. In other words, the 0-1 part of the connection, the d-bar operator, is just the standard one for that holomorphic structure. And so there's no 0-2 curvature and there's no 2-0 curvature. And so what you've got basically is 2 out of 3 of your anti-self-duality equations for free. And the question is how to get the third. Okay, so there's one way, which is twistors. And it exploits the fact that the R4 has 3 complex structures. So it's a quaternionic, it's the quaternions, basically. So it's got 3 complex structures, I, J, and K. In fact, a whole Riemann sphere's worth. So those linear combinations. And changing the complex structure rotates these self-dual forms amongst themselves. And so the connection is going to be anti-self-dual. It's going to be holomorphic for all of the complex structures. So the sort of picture is you've got an R4 that's sitting here. You've got a Riemann sphere that's sitting here. Then you've got copies of R4 that are sitting above it. So I'll give this one to I, I'll give this one to J, and I'll give this one to K. The complex structures are acting on these planes. There's a complex structure on the Riemann sphere, and then the whole thing that you get is in fact going to be P3 minus a line. And so basically, if you want an anti-self-dual here, you're going to have something holomorphic up here. And then you put in boundary conditions, and that compactifies it to P3C. But you have all sorts of involativity, reality conditions, and so they're a little bit hard to describe directly. On the other hand, there's this lovely construction of the ADHM construction that basically gives you the holomorphic bundle in terms of matrices, and from then you can indeed compute. And it's described, gives you very, very explicit descriptions of the actual solutions. There's another way, though, of dealing with this 2 out of 3 business, is the direct approach. So you can fix one complex structure and you minimize energy on the metrics. So you remember, you're choosing a metric, a Hermitian structure. So you can fiddle with that. And the idea is then you can get that third piece of the curvature to 0. And typically that's done through a heat flow. It's a tricky equation. There's usually some form of stability. You're thinking of a variational problem. And so you're flowing down, taking a downward flow on the energy. And you want to hit a minimum, and you don't want to flow past. And so you need some form of stability of the thing to assume that the minimizing flow converges. And here it ends up being enforced by a trivialization of the bundle infinity. Here meaning on this R4 case. So it's to be emphasized, this doesn't give you the actual solution. Your energy flow is a black box, so you don't know, but it does give you the moduli. So one stable complex structure gives you one instanton, one solution. And so on R4, it's the theorem of Donaldson's that instantons give you bundles on P2, trivial and fixed line at infinity. So this whole story has been developed over the years quite extensively, and in fact by now quite a while ago. And for general manifolds, if your manifold is what's called hyperkähler, so it has a metric whose holonomy is SPN, or it has three complex structures, it's Kähler in three different ways. These will have twister spaces, and in 4 dimensions, you'll get instantons from this twister construction. For Kähler manifolds, there's a long series, it's a sort of Kobayashi-Hitchin, conjecture or principle or thing. The first proof of one case is by Donaldson, Yao Nulenbeck, Simpson, and various other people over the years have generalized this in various directions. But I should mention that the first, though not terribly explicit, they don't really use the variational approach, occurs in the work of Narasimhan Seshadri of bundles on a Riemann surface, showing that they correspond to flat unitary connections. But in general, again, you get this sort of 2 out of 3 from the holomorphic structure, then you need stability to flow to the anti-self-dual solution. And the general theorem is stable holomorphic bundles, gives you what's called a Hermitian Yang-Mill connection. So that's the general case. Okay, well now you can do some reductions from R3, and again this sort of scheme appears. You get the full solutions. Sometimes they're solved using the sort of twister type constructions, and sometimes they're not solved, but you can understand the moduli just using this one complex structure. So I'm just going to give you some examples, and we'll see that there are some nice cases of curves that come up. So the first example is monopoles on R3. This is, basically Nigel Hitchin laid out the sort of almost complete theory in for gauge group SU2. Simon Donaldson did the sort of key point in understanding the moduli. Michael Murray, and then Michael Murray and I did some work in the classical groups, understanding these things for the classical groups. And there's a very nice paper of Stuart Jarvis that sort of gives you the moduli spaces for all groups. So what do you do for a monopole? Well, you impose a time translation invariance. So you've got an R3, and then in time you're just, it's supposed to be invariant there. So you get a connection in the R3 direction, and a Higgs field phi, which is here just basically a section of the endomorphism of a bundle. If you're thinking of an UN, so maybe I'll just use the Lie algebra. So it's sitting in the Lie algebra, and your anti-self-duality equation just becomes this in 3 dimensions. What you do have is different boundary conditions. So the connection decays, but on the other hand, the phi tends to a unique coadjoint orbit or adjoint orbit in UN. So in other words, thinking of UN, it's the a fixed eigenvalues at infinity. When you fix one complex structure, so just set this, and then you've got the third coordinate x3, and you put in the time as but that, remember, that time is just sitting there as a dummy. The 0,2 component of the anti-self-duality becomes, well, the d bar operator for thing, commutes with a sort of radial operator, or not radial really, but an operator along the x3 direction, just a standard ODE, which you think of as a scattering equation in the x3 direction. And so if you solve this equation, it's an ODE, and you solve it for all initial conditions in that plane, so you solve it in this x3 direction, you've got a holomorphic bundle on that z plane, the x1 plus ix2. And if you do this for all complex structures, you get a complex structure, complex bundle in twistor space. So the sort of picture is that you've got a, here's P1, and then you've got the tangent bundle of P1, which you can think of as the oriented lines in R3. Okay, so you're fixing a direction here, say 0, and these will be that line of, this will be that line of directions, and then orthogonal to that, have the direction 1, and that'll be another plane of direction. Sorry, so it's a complex line, but it's a real plane of lines all parallel and going off in a particular direction in R3. So in R3 you have this picture, and this this is of course a complex surface, so we're sort of running out of dimensions, but this line here is in fact this plane here. Okay, so what you get is a complex bundle. Now, unfortunately, that's not telling you much. If you just look at line bundles on TP1, it's actually an infinite dimensional space. So there's not much there, but what saves you in the end is the boundary behavior. And so the boundary behavior is that phi, remember, is conjugate to, say, a diagonal matrix. And the asymptotics are such that, well, when you solve so when you solve, just think of it asymptotically as d plus alpha, where alpha is a constant, s equals 0. You're getting e to the, or d, say t. You're getting e to the minus t alpha as a solution. And so what this is doing is when you're solving that scattering decay, you're getting different decay rates for different solutions. And so if you solve it uniformly, you're getting a flag. There's a line that's decaying fast, a two-plane that's decaying slightly less fast, and so on. And you've got two directions to do it. You can go to plus infinity and minus infinity. And so these flags are generically transverse. And they fail to be at a finite set of points in the z-plane. So let's sort of try to sort of see that. So here's, again, my base P1. And now I'm going to draw. So this is a sort of mix of complex and real coordinates. So here's my z-plane. And I've got a finite set of points where so this is one direction, where the flags fail to be transverse. But now I've got a family of directions to vary in. And so what I'm going to get are curves. Now, why should I get n-1 curves? Well, I've got the line at plus infinity intersecting the codimension 1 plane from minus infinity, different from, sorry, this shouldn't be phi, it should be 0. different from 0, so it's here. And then I've got the 2-plane intersection, the n-2 plane, different from 0. And these are giving me different curves. So again, you're seeing these spectral curves appear. And that and the sections of line bundles along these spectral curves determine the monofold. And that's work of Michael Murray. And in some sense, all is computable from this. So you could actually sit down and sort of get out theta functions and things on the line bundle. It's quite an arduous task, but it does encode the actual monopole. For the moduli, of course, you just need one direction, right? Because that's this principle of fixing one complex structure. So you just need these flags, or this scattering, or this intersection of flags in one direction. And the way you can think of this is as follows: that you're starting out at -infinity, and you're looking at what's happening at +infinity. Oops, sorry about that. And you've got your flag up here. And here, basically, you think of your because it's asymptotically flat, you might as well choose a basis. And so you solve your scattering equation. So you sort of transport this flag through.
Jacques, let me interrupt you just a second. Yeah. We seen a question from Chris Krylova. It's not in chat, but he's got his hand raised. Chris, could you speak up for a second and ask your question?
Sure.
Chris?
Hello?
Hello, do you hear me?
Yes.
Oh, yeah, we do.
Actually, just a comment. So our chat was disabled, and also I think it was hard to unmute myself. So just to keep in mind that people can't really talk to themselves. But the question that I had was actually much further back for the anti-self dual, where you had f equals to Hodge derivative of phi. Why was it in 3 dimensions?
Sorry?
For the anti-self dual further
back.
It's
just that your equations, now that you're thinking of the Hodge operator in 3D, not in 2D. So in 3D, it's always takes you to the complementary direction. So the star will take 2 forms to 1 forms. And if you think the covariant derivative of phi will be a 1 form with endomorphism values, and the curvature is a 2 form with endomorphism values.
Okay, thank you.
Yeah, okay. So, yeah, for moduli. So now what you're doing is you sort of take your flag at -infinity, and you sort of carry it through, and it's going to give you, I should be able to use different colors here, but I think this is almost beyond me. Oh, well, nice try. And so it'll give you a sort of varying flag as you go off. And in fact, if you're sort of scattering from way out at the edge of your planes, it should be, it's missing the sort of essential part of the monopole, which is sort of in the center here. And it should just be sort of constant. And so what you're getting, you see, is this, you follow this flag from -infinity up to this trivialization at +infinity. And what you get basically is that your information that determines the monopole is just a map from the Riemann sphere to the flag manifold. So the Riemann sphere is here, it's this, C, and you add in infinity. And the target is essentially what's happening to this flag with respect to the sort of standard basis. And that's this UN mod T. So that's the story here. Its proof was generally through rather indirect construction, to which I'll come back later, of monopoles using through the geometry of an integrable system on these spectral curves, in fact. But there's a nice direct proof, thanks to Jarvis, again using this variational idea of minimizing the energy of a matrix. So the rational map allows you to set boundary conditions, and then you can minimize the energy. Another example that I worked on with a Charbonneau a while back was the monopoles on a Riemann surface across the circle. So here again, you want to think of, you'll have a Riemann surface sigma, which I'm going to draw as a little plane here. And you've got a circle which unfortunately I'm going to draw as a segment, but morally you're taking this end and sort of gluing it back to here. And this is a compact manifold. So monopoles don't live well. They're not happy on compact manifolds. They tend to be sort of constant, or they're boring. And so what you do is you allow the singularities that are precisely of the type studied by Dirac in his 1931 paper. So they have poles. And so you can sort of scatter through these poles. You again have this scattering equation. So theta is your circle action. This is the circle piece. And you've got the d bar operator on the Riemann surface. And this says that this scattering operator preserves holomorphic structures. So you basically, as you're sort of moving, say, from here to here, you're keeping the same holomorphic structure. But then something's funny is happening when you go through the singularity, is that it introduces a twist, a singularity, which is basically this form. So if you should think of the monopole, at least in the sigma direction, as being located at z equals 0. And it's introducing either zeros or poles, basically. And so what it's doing is you're sort of going through this, say one of the poles here, is you're getting what's called for geometers a Hecke transform of the bundle. And so it's introducing a little twist. It's changing degrees, it's changing things. And in fact, this was used by Kapustin and Witten in their paper on geometric Langlands to sort of model the Hecke transform in terms of monopoles. Now they're using it with different boundary conditions. They're just going basically on an interval. So we sort of closed things up and went onto the circle. So what do you do? Well, you solve this scattering thing. You go all the way around. Go through. Sometimes you hit a monopole, sometimes you don't. And you come back to where you started. And so what's solving, when you solve the scatter, you get a map from E to E, where E is just the bundle, say at a base point, a base sigma, say here. Okay. And you've got well, it would have been just an isomorphism if there were no singularities, but then you wouldn't have had a monopole. It's going to be instead a meromorphic automorphism. So it's mapping E to E, except when it hits one of these points, it introduces it introduces a little a twist. If it misses the points, it's just an isomorphism, and if it's not, it introduces either a zero or a pole. And so that's your object. And what you can show, again, is using this energy minimization idea, is that the moduli monopoles is indeed the set of stable pairs. So the stability here is there should be no phi invariant subbundle of big degree. The degree is a strange one. It's actually the integral over the circle of the degree on each slice sigma. So you take the degree. As you go through these special points where the singularities are, the degree pops. And so you've got the length of the intervals between two singularities that comes into the definition of degree. But then your moduli, and this is kind of fun. So here I was promising some curves. So your moduli will also be a set of curves given by the determinant here. And you'll get a line bundle as a co-kernel. In fact, this is a construction that comes back later. If you think about it, you've got, here's sigma. I'm going to put a P1 here. And in the product, I'm going to have 0 and infinity that are somehow privileged points. And I'm going to get a spectral curve, which is this curve here. And you notice the points of intersection with 0 or infinity are where this phi ceases to be an automorphism. I mean, where the singularities are. But basically, you'll get S, and the co-kernel will live on the, oops, what have I done? The co-kernel L will live on this spectral curve. And basically, you're going to get E is going to be the algebrogeometric pushdown of L. And phi is just the pushdown of the multiplication by the Z coordinate on P1. So multiplying by the coordinate on the sheaf L sort of acts above here, and when you push it down, you get phi again. So you're getting a sheaf that's trying to look like an integrable system. It will be when the base curve is genus 1. For genus higher than 1, I'm a little bit confused. We don't really know what should be there. There's another example where the curves come, and this is in fact linked. Where instantons on the R cross the circle, cross a torus. So you have an infinite direction. And you've got at the ends, essentially S1 cross a torus, which is, of course, R3 model lattice. Now, it could be a 3 torus, except we want that S1 to be sort of separate. Okay, and you get a decay condition at both ends to sort of get finite energy. And the decay is that basically in this direction, everything's asymptotically flat. So you've got a flat connection on S1 cross sigma. So minus infinity, plus infinity. Holomorphically, what do? You compactify. C star, which is a radius across a circle, to the Riemann sphere. So you add in other words, a copy of sigma at both ends. And you'll get a bundle on P1 cross sigma. And the question is, how do you analyze this? Essentially, because you're asymptotically flat at both ends, what you're going to find is that on a generic thing in the middle, your holomorphic bundle is going to be a sum of lines, of line bundles. So in other words, Li are degree 0. And there's a very nice algebrogeometric way of picking these out. And what it uses is that H1 of sigma L, a line bundle of degree 0, is 0 unless L is trivial. Okay. So how do you pick out these LIs? Well, you take this sum here and you twist it. So you twist by varying, say, L, and I'll put a dual here, L star. Okay, and then you look, you find at the points, points where H0 or H1, sorry, L star tensor E different from 0. Okay, points, I should say, instead of points, I should say the L stars. Okay, and that'll be, well, it's going to happen at L1 star, L2 star. And so you're able to find out what the sum is. Now, what this amounts to in more sort of correct or concrete term or general terms is to do what's called a Fourier Mukai transform. So you start with your bundle on P1 cross sigma, you lift it to P1 cross sigma, cross the dual torus, so the degree 0 line bundles. And then there's a universal line bundle on sigma cross sigma star called the Poincaré bundle that basically realizes all of these L stars in turn. And then you take, I suppose it would be a direct image, excuse me, first direct image. And that's the process that will give you, it'll give you what? Well, it'll give you a spectral curve. You can prove using the Riemann-Roch-Grothendieck theorem that it's got a bidegree that basically encodes both the rank and it's the second Chern class of the bundle. And the nice thing, and this is a theorem of Mukai, is this process is involutive. So you can sort of apply it getting backwards. So it goes both ways. There's some twists, but they're kind of easy to deal with. So again, you're getting a curve and a degree. Now, what's also interesting is, oops, excuse me. No, that's not what I want. This is what I want. Good. I had these two cases, remember, monopoles on sigma cross S1 and instantons on R cross S1. And in fact, they're non-transforms of each other. So maybe I can tell you a bit about what this is. So you start with a self-dual bundle on X. You twist by basically line bundles, flat line bundles in this case. So a set of flat line bundles. You solve the Dirac equation, and you get a bundle F over the set of flat line bundles. And then the miracle is basically, in these cases at least, that if you start with an anti-self-dual thing here, you get an anti-self-dual thing here. In other words, what you do is that F is sitting inside some function space, typically the L2 functions, and you project the flat connection. And that's giving you it's going to give you an anti-self-dual solution. So it's not so much a recipe as a heuristic, because you have to adjust the boundary conditions and things like that at each time. But these two cases are in fact linked. And so it comes to me with another thing that comes from basically starts its life with monopoles, but since acquired a life of its own, where you take the anti-self-duality equations and reduce by 3 translations. So here you get a connection, but now along a line. And your 3 other components just become, again, skew Hermitian matrices. And the anti-self-duality equation is just this ODE. And you can, again, combine it in a sort of way that's compatible with write it in a way that's compatible with the twister. Whereas you just introduce this parameter, this zeta here, to be thought of as sitting in P1. Really. Well, it's in C, really, but anyway, let's put C for the moment. And then these equations become a lax equation. So what is this saying? It's saying that basically you're getting that dA plus bracket of B with A. Don't forget that the nabla here has a connection component, is 0. So what does that mean? It means it evolves, or A evolves, by infinitesimal conjugation. Okay, which means that the spectrum is invariant, which means there's an invariant spectral curve. So here the curve is independent of the flow parameter S. I'll put an S here, I guess, for the flow. Okay, and indeed, these equations, well, they were sort of worked on extensively in various people working on integrable systems and Riemann surfaces. And you can solve these using basically data functions. You can even think of these equations as a generalized Hitchin system, which I'll come to later. So you have the sort of self-swallowing aspect of this whole theory, which comes into play. There's a paper, I'm afraid I forget the other author, but it's Ercolani is one of them in the late 80s that actually solves these Nahm equations in terms of theta functions. So what's the holomorphic data? Well, again, this principle of just choosing one of the complex structures, so you set z equals 0, and you just get basically a one simple ODE, which is just telling you that in fact this sum T1 plus IT2 is covariant constant. So your invariant of the flow is basically just a matrix. You can go to a gauge where the connection term is 0, and then the other term, this T1 plus IT2, will be just a constant matrix. So there's not much there. And the answer to what happened is in the boundary conditions. So just for example, and they can be quite weird. For monopoles, the non-transform will give a solution on a sequence of intervals. So you have a bunch of intervals like this. And it's a peculiarity, and it's linked to the sort of the index of a family of Dirac operators. The number of solutions will change from interval to interval. So you're going to get matrices of different sizes. I put an N here. And just to give you an idea what these boundary conditions can look like, they're quite strange. So at a point between two intervals, so you've got a sort of big side where the NU is bigger and the smaller size. And you're going to get a block which is of the smaller size. The other block, the other diagonal block, is going to have a pole. And the pole has to be the components of an irreducible representation of SU2. So in the standard representation was Pauli matrices. And there's some vanishing also that you impose for these terms. And so the matching condition is the small sign. Oops, it doesn't want to move anymore. No? Oh well. There we go. Whoops. No. Sorry. Maybe it's time I shut up. There we go. Okay. So the on the small side, it's the solution from the small side is the piece that. Oops. No. Come on, behave. No. Okay, so where was I? Yes. Okay, so as I was saying, the solution on the small piece, this block here, corresponds to this, and it's the solution from the other interval. And the point is you can have different boundary conditions for nilpotent orbits, instantons on a Taub-Nut space too. So there's a series of papers by Cherkis that deals with these cases, again obtained by a non-transform. And why would you bother? Well, is the holomorphic data that gives these things is usually very easy to describe. So for example, these solutions to Nahm's equations were used to link them. You could link them quite easily, the ones for the monopoles, to rational maps. But then if you think of them as solutions to the full equations, which you can, again, using this variational idea of flowing to a solution of the full equations, you're going to get a hyperkähler metric. So you can show that various things have hyperkähler metrics on them, which is kind of nice. Okay, I should mention, perhaps in closing, that there's a whole sort of parallel story of the anti-self-duality equations linked to integrability in the sort of PDE sense, equations that fit into an integrable hierarchy. So these equations also will fit into the Hitchin systems as lax equations and things like that for what's called finite gap solutions, so solutions associated with Riemann surfaces. But they also just appear as reductions of the anti-self-duality equations. And there are various people, and I've just named a few, and I'm certainly missing some. But there's a paper, a 2003 paper of Ablowitz and Clarkson, showing that basically by sort of taking various symmetries and sort of taking solutions invariant under those symmetries, you get all these classical integrability thank you.
Jacques, let me interrupt you for just a second. There was a question in the chat from Rajesh Kumar, who says, and I quote, "This system, can we check the stability by using Lyapunov's method, or can you use some other method for stability?" The chat's been up there for a couple of days.
The stability here is an algebrogeometric one. It's linked to the. It's a very curious thing. You see, you have these heat flows, and you'd have their stability, which is basically convergence to something finite. And you have the algebrogeometric stability, which is linked to the geometric invariant theory constructions of these spaces. And that geometric invariant theory question is basically you're building your moduli space as the quotient of something simple by an algebraic group. And you need, for this thing to be well parameterized, there should be invariant functions. And so the stability is basically saying that, and because you're looking at it, sort of algebraic functions, homogeneous functions, basically, because you're doing it typically in Pn, you're looking at things that stay away from the orbit in the origin. So you've got an orbit of the group, and you ask, well, does this stay away from the origin? Because if it goes to the origin, then the only invariant functions are zero. And that's bad, because you've got no way to parameterize them. So you throw away the things that go to zero, basically. And so there's that stability, which is the algebrogeometric one. And then there's the stability of these heat flows. And the heat flow itself is very interesting, because the way it gets manifested, if you don't have stability, is, remember, you're taking a flow in a space of metrics. And the metrics degenerate. And this is in this perhaps clearest in this paper of Uhlenbeck and Yao. They degenerate, and the way they degenerate is they degenerate into projectors. So you know, eigenvalue, you know, metric, you know, it's up to conjugation. It's you know, a series of real numbers. And so some of those numbers go to zero, basically, and you get a projector instead of a metric. It's not quite a projector, but it's behaving like it. And it projects onto this subbundle that has too many sections. It has too many, it has this positivity property that you exclude in the algebrogeometric section. So the link is extremely subtle. I can't say I really understand it, but it's very pretty. But it's not really like, well, maybe I suppose if you're you know, maybe it's my lack of understanding of the Lyapunov stability. But it's if it is that type of stability, it's quite an indirect Lyapunov, and I'm not sure Lyapunov would have recognized it.
Thanks.
Okay. Anyway, that's more or less what I had to say. Sorry, I'm disappeared. Oh dear. So there we go. So you get all these equations. There's some beautiful papers on the Pain-Levé. The Pain-Levé is one of those ones where it's halfway between an integrable flow and something else. There are bits of the Pain-Levé equations that are trying very hard to be algebraic. And there are other aspects in which they're totally refusing to. So for example, each of these Pain-Levé has a sort of tame cousin that corresponds to flows of line bundles and some very classic things with an invariant elliptic curve. And these seem to be more associated to curves that are varying, and yet they do have some interpretations in terms of compact surfaces. So they're quite mysterious. But again, they occur in this as reductions. And it's explained, I think these mostly papers of, is it Mason and Woodhouse, actually, where this subject is explored. But it's quite an intriguing aspect. And it's just on the boundary of curves. Okay, so I think I'll stop there then. So thank you for your attention and patience. And it's quite late in India, I gather.
That's all right. Thank you very much for a wonderful talk. Let's everyone thank Jacques with our reactions things. And let me ask, yeah, someone already has their hand raised. Or sorry, I think Chris, could you unmute yourself and ask your question?
Can you hear me?
Oh, we can hear you now.
Yes.
Okay. I was actually wondering, you mentioned twisting several times. The way I think of it is more like topological twisting, like from string theory, if you're familiar with that. I was wondering if you could just elaborate on how have you did it during the lecture.
Okay, sorry. I think that the twisting I was referred to was just tensoring by a line bundle. Okay, so it's really more like simple. It's just that. Yeah, no, it's just that you're tensoring. In fact, for this non-transform, you're tensoring by flat line bundles. And so you've got a connection on, you're starting with E has a connection, you're tensoring with L that has a connection, you've got a connection on E tensor L. The L one, this line bundle, the connections is flat, so that's kind of easy. But then you take the Dirac operator on E tensor L and solve that. Okay, thank you. Yeah, so that's it. And the point is it's giving you a vector space of solutions, typically on a compact manifold. And that vector space is then varies with the L that you tensored with. Okay. And that's the sort of non-triviality of the.
I'm not seeing any other questions at the moment. So let's thank Jacques again.